Hello everyone. This is another video on spring/mass systems. But in this video, we're going to be looking at the scenario where a spring is hanging vertically, then a mass is attached to the end of that spring, right, allowing it to stretch so far into equilibrium position. But instead of letting the mass hang freely, right, maybe pull it down from equilibrium or push it up from equilibrium and let it go, a couple other forces might come into play. There may be a dampening force, which you saw in my last video on free damped motion. But on top of this dampening force, there may also be a driving force. Alright, thus the name driven motion here in the title of this video, driven motion example. And this driving force will change with time. It'll be a function of time, and a force that is pushing the mass in different directions at different times. So that'll be added to the sum of all the forces on the mass, and we'll get a new kind of non-homogeneous differential equation here in a second. Alright, so this picture I actually drew up in the last couple videos, right? I drew it in the first video on free undamped motion, if you've seen that. And then I added a dampener. The mass could be dampened by some liquid or some medium, something that slows it down as it travels through. But now on top of this, we're going to have a driving force that'll go, so a driving force. Now I'll put this up and down because it's going to go like kind of with the mass against the mass at different times. It's going to be called F of t. Right, it's going to be some force that changes as time goes on. So sometimes the force could be going with the mass, sometimes it could be going against the mass. So I'm just going to say F of t. Right. All right. And as before in the previous couple videos, the positive direction will be considered going down, the negative direction will be considered going up in an upward motion. So any position below the equilibrium position will be positive. Any position above the equilibrium position will be considered negative, right? Where x of t represents the position of a mass at time t. All right, and the mass can be in either kilograms or slug. Time is in seconds, and the distance that things are traveling in, the positions, are either in meters or in feet. And that's it. Okay. And I guess forces too. Forces will be either in newtons or pounds, right, depending on what system you're in. Okay, so then the differential equation that comes from this is just like in the previous two videos, where it's coming from Newton's second law of motion, that the net force acting upon an object is equal to its mass times its acceleration. So I have mass times the acceleration of this object, which, if x is representing position, then the second derivative of x with respect to time is the acceleration. And this mass times acceleration should be equivalent to the net forces acting upon the object. Well, there was the negative k times x, right, which resulted as from Hooke's law. Right, the force of the spring acting in the opposite direction of the motion of the object. And this k is a positive constant, right? This is the spring constant, which again you can find from Hooke's law, that force equals K times S, where S is the, equilibrium amount of stretch in the spring when a mass of size m is put on it. All right, then another opposing force is the damping force, if there is any damping, so another minus here. Minus beta times dx dt. All right, and this beta times dx dt is called, the damping force. You saw this in my last video, hopefully. And the damping force is proportional to the velocity of the object as it moves through that medium. And then beta, right, the beta itself, another positive constant, is called the dampening constant, or damping constant, damping. All right, and now something new, right? This was the equation when we had free damped motion in the last video. And again, the reason it was called free is because you just let the mass go and move up and down as it does. But now on top of these forces, we have this driving force, which is going to change as time goes by, this f of t being added on here. So plus, and again, some function of time called the driving force. Right. Okay. So that changes this equation from a homogeneous to a non-homogeneous second order equation. Still linear though, right? And we have seen in previous videos, hopefully you recall, how to solve non-homogeneous linear equations. Alright, let me just put this in the form that I would like. So we have the mass times, x double prime, right, which is the second, the acceleration of the mass, plus beta times x prime, right, plus that damping force, plus k times x, the spring, basically the spring force, equals f of t, right, equals this driving force. Right. So here's the form that the differential equations for these driven motion spring problems will look like. So we just need to determine the m, right, the mass in slug or kilograms. We need to figure out, unless we're told, the beta, right, the dampening constant. We need to figure out, or unless we're told, we need to figure out the k, the spring constant. And I'm pretty sure we're going to be told each time what the driving force is, how the force changes that's acting on the mass over time, the f of t. And then of course, this will also be subject to initial conditions. And with the differential equation and the initial conditions, you then solve that initial value problem, find the function x, that position function, or that equation of motion. All right. So I'm only going to do one example here. I know I normally do more than one, but if you can follow this one example, you should have a pretty easy time with others like it. All right, so I have it not written down, and just pull it up on a ebook for differential equations text that I've been looking at. So here we have a mass weighing 16 pounds. Remember, weight is not mass, weight is force. So I need to find the mass from this. And if this is in pounds, then the mass should be in slug, right? If they had newtons for the force, the weight, then the mass would be in kilograms. You'd be in metric, but here we're in imperial units, English units. So a mass weighing 16 pounds stretches a spring 8/3 of a foot, 8/3 feet, right? 2 2/3 feet. This sentence here is going to enable me to find the value of K, the spring constant, using Hooke's law, but we'll get to that in a second. And notice the stretch is in feet. Right, it should be. The mass is initially released from rest, right, so the initial velocity is 0, rest, from a point 2 feet below the equilibrium position. Now remember, below equilibrium position is a positive position. And the subsequent motion takes place in a medium that offers a damping force that is numerically equal to half the instantaneous velocity. So that's that beta, half dx dt is the damping force. Find the equation of motion if the mass is driven by an external force equal to 10 times the cosine of 3t. That's the f of t there. So they've given me a lot. Okay, so going back to my paper, they said the weight of this thing was 16 pounds. Remember, the weight of an object is its mass multiplied by the gravitational acceleration constant, which if I'm in pounds, I'm going to be using 32 feet per second squared. Right? If they gave me newtons, then the gravitational constant would be 9.8 meters per second squared. Right? So just again, pay attention to units. So in dividing by 32 here, we get the mass of this object is 16 pounds divided by the 32 feet per second squared, leaves me with slug, half a slug. All right, so m is a half. And they told us also, remember Hooke's law, is that the force acting on a spring is equal to some constant times s, where s is the amount of stretch to equilibrium, the amount of stretch on the spring with that mass on it. So the force is again 16 pounds equals K times, and then the stretch they said was 8/3 of a foot, or 8/3 feet. And I divide by 8/3 feet and we get our spring constant, K. Now divided by 8/3 is times 3/8, so that would be 6, right? Because 8 goes into 16 twice, times 3 is 6. This is 6 pounds per foot, but just 6. There's the spring constant coming from Hooke's law. So I've got m is a half, K is 6, and finally the beta. Well, they told us, right? They told us that the mass will be going back and forth through maybe some liquid or some medium, and the medium it's going back and forth through offers a damping force that is equal to half the instantaneous velocity. Right? It's equal to half instantaneous velocity, which is dx dt. So the beta, that dampening constant, is 1/2. So I got half for the mass, half for beta, and 6 for K. And then finally we have this f of t, the driving force. Right? It's this external force, and they said if it's driven by an external force of f of t equals 10 times the cosine of 3t. Alright, so I'm going to put all this in and we'll get our differential equation. Then I'll also state the initial conditions and we'll go through and solve the initial value problem. Right, but this is half the battle here, setting up this equation. If because after you set up the equation and initial conditions, solving the thing should be probably the least of your worries. So I have half of x double prime plus half of x prime plus 6x equals 10 times the cosine of 3t. All right, putting all that stuff in. Okay. So hopefully, then the initial conditions. I'm going to write IC for the initial conditions. Now they said it was initially released from rest. So x prime at 0, right? The velocity x prime at 0 is 0. Right? That's what it means to be at rest. You're no velocity. And it was initially released from rest at a point 2 feet below the equilibrium position. So the initial position, x sub 0, not x prime, x sub 0 is 2, right? And this is 2 feet below the equilibrium position. A positive position. All right, and being a second order equation, these two initial conditions should be enough to find a solution to this initial value problem. All right, so now we're solving this IVP here. All right, this initial value problem. All right, so first we'll find the general solution of our differential equation. So remember, for a non-homogeneous, first we find the solution to the corresponding homogeneous equation, or the associated homogeneous equation. So I'll write that up first. Associated, I'll just put homo for associated homogeneous. That'd be half x double prime plus half x prime plus 6x equals 0. And then the general solution to this will be called, the complementary function. And hopefully all this sounds familiar. I'm going to multiply through by 2 here, make it a little nicer looking. So x double prime plus x prime plus 12x equals 0. And then we have one of those homogeneous equations with constant coefficients. So I would let x equal e to the mt and put it in here, and we'd have, here's our auxiliary equation. I'll just put AUX. M squared plus m plus 12 equals 0. And then we could solve this, with the quadratic formula or completing the square. If you've seen, videos of mine in the past, I prefer completing the square myself. And then I subtract 12 and then complete the square, add a quarter to both sides, and this would be negative, 47 quarters. That's 48 quarters, right? And then we have m plus a half squared equals negative 47 fourths. So my roots would be negative 1/2 plus I times the square root of 47 over 2. And then minus that, right? So let's do m1. So my roots are complex conjugates. Negative 1/2 plus the square root of 47 over 2 times I. Negative 1/2 minus the square root of 47 over 2 times I. All right, so the my complementary function, right, the solution of this, the general solution of this associated homogeneous equation, complementary function xc, right, this is x's, of t equals some, so again, this is some constant, c1 times e to the negative half x, or sorry, t, negative t over 2, times the cosine of the square root of 47 over 2 t, right, plus some other constant, c2, times e to the negative t over 2 times the sine of the square root of 47 over 2 times t. All right. So that's what, again, just the solution of the homogeneous version looks like. Right. Now if you go back to the non-homogeneous, we can use annihilators. All right. So using differential operator D, D equals, d dt here, the derivative with respect to t. The first equation would look like the following. We'd have half d squared plus half d plus 6, right? This applied to the function x equals 10 cosine of 3t. And then you may recall from previous videos of mine on annihilators that the operator d squared plus 9 would annihilate 10 times the cosine of 3t. And you can check that, take the second derivative of this and then add 9 of it, and you'll get 0. That's what it means to annihilate. So I apply this annihilator to both sides. So we'd have d squared plus 9 times the half d squared plus half d plus 6 applied to x, and that should be equal to 0, right, if I apply that annihilator. And then we basically have a homogeneous equation again, right, 0 on one side. And you already know what the solution is from this. You already know what's coming from this. This was, I got this from the homogeneous version, right? So it's from this annihilator that comes the form, we get the form of the complementary solution, x sub c. And then from the annihilator, d squared plus 9, we get the form of a particular solution to our equation called, I'll say, xp. All right. And I'll tell you right now, again, d squared plus 9, if you were to look at, x double prime plus 9x equals 0, basically. If you were to look at x double prime plus 9x equals 0, right, that's giving me the form of this particular solution, the form of the solutions to that kind of an equation take. And it'd be some constant a times the cosine of 3t plus some constant b times the sine of 3t. And now I need to find a and b to get, a particular solution here. All right, so now we go back to, and I'm going to be going back to the original equation. So I need the first derivative and the second derivative of this. So xp prime would be negative 3a times the sine of 3t, then plus 3b times the cosine of 3t, and then xp double prime here would be negative 9a times the cosine of 3t minus 9b times the sine of 3t. Right. And then I substitute these into the original equation. Right. And then I should be able to find a and b by equating some coefficients. Right. So subbing, to be half of x double prime. Alright, I'll say half of xp double prime plus half of xp prime plus 6 times xp. This should be equal to 10 times the cosine of 3t. And then I'm going to equate some coefficients on the other side, on another page here. So basically I'm going to get all the cosine of 3t's together and the sine of 3t's together. So if you look at all the cosine of 3t's, I have half of, negative 9 halves a, then plus half of the xp prime, so plus 3 halves b, and then plus 6 of xp plus 6a. Those are the coefficients added together of cosine of 3t. And then you have the stuff with the sine of 3t as well. So you have half of xp double prime, so negative 9 halves b, then plus a half of xp prime, minus 3 halves a, and then plus 6 of xp, so plus 6b. And this all needs to be equal to 10 times the cosine of 3t. And then from this we get a system. I hope this all sounds familiar, right? It feels familiar solving non-homogeneous equations, finding particular solutions. So this needs to be equal to 10, and this needs to be equal to 0, right? Because the coefficients of the cosine of 3t on both sides need to be the same, and the coefficients of the sine of 3t on both sides needs to be the same. So we have what? This is 12 halves a minus 9 halves a. So that's 3 halves a plus 3 halves b must be equal to 10. Alright. And then this, we have, negative 3 halves a, and then 12 halves minus 9 halves plus 3 halves b must be equal to 0. Alright, so this equation here tells me that a must be equal to b. Right? A must be the same as b. And if a is the same as b, and just replace b with a here, we'd have 3a. Right? We'd have 6 halves 3a equals 10. So a equals 10 thirds and b equals 10 thirds as well. And we get our particular solution. So xp is equal to 10 thirds times the cosine of 3t plus 10 thirds times the sine of 3t. That's not the answer, I'm just putting it in a box. So now we go back to the original homogeneous equation, all the way back up here. Right? The original homogeneous non-homogeneous equation. Go back to that, and the general solution to that equation looks like the following: x sub t equals, now remember, it's the complementary function plus a particular solution. So the complementary function we had was this here. All right, so it's this here. I'll pull out e to the negative half t. So e to the negative half t times the quantity, some constant c1 times the cosine of the square root of 47 over 2 times t plus some constant c2 times the sine of the square root of 47 over 2 times t. There's the complementary function. Then plus some particular solution. Which, both of these, I'll pull out the 10/3. 10/3 times the quantity cosine 3t plus sine of 3t. Alright, and there you have it. Now this isn't the end. Alright, this isn't the end. But that's the general solution of our non-homogeneous equation, of this equation here. What I need to do now is figure out what solution satisfies our initial conditions. So I need to find C1 and C2. So I think I can find one of them pretty quickly. All right, remember the initial position. All right, I have the initial initial conditions up here. All right. X of 0 was 2. So let's use that. All right, initial condition time. X of 0 was 2. So that gives me this following equation. 2 equals, now when I replace t with 0, this would be 1 times, the quantity C1 plus 0. So this would be C1, this whole big term here, plus, then plus 10/3. Right, because the cosine of 0 plus sine of 0 is just 1. And then 10/3 there. So then subtracting 10/3 from both sides, we'd get C1 equals, 6/3 minus 10/3, negative 4/3. Right. C1 equals negative 4/3. And C2 will be a little trickier, because I'm going to need to use that other condition, that x prime of 0 equals 0, right? It started off at rest. Well, I'm going to replace C1 here with negative 4/3 right now, since I know it is negative 4/3. And then let's take a look at x prime. All right, this will be a doozy. So the derivative is going to be, the first one I'll do the product rule. So you have e to the negative half t times, the derivative of the second one would be positive 4 root 47 over 6 times the sine of square root of 47 over 2t, and then plus c2, or plus the square root of 47 over 2 times c2 times the cosine of the square root of 47 over 2 times t. Alright, I'm not done with the product rule yet. Then minus basically half of this. So minus half e to the negative t over 2 times negative 4/3 times the cosine of square root of 47 over 2 times t plus c2 times the sine of the square root of 47 over 2 times t. Alright, and then we have here some pretty easy ones. In both of these, a 3 would come out, and this one negative 3 would, this one positive 3 would, so pull the 3 out, you'd have then plus 10 times sine of 3t, or sorry, cosine of 3t minus sine of 3t. Right. Okay. So there's the derivative. And then I know that it's at rest to start with. Right? So x prime of 0 equals 0 leads me to this equation. We have 0 on the left equals, so putting in 0 for t, you have 1. That's nothing. We'd have the square root of 47 over 2 times c2, and minus a half times -4/3. Alright, because remember cosine of 0 is 1, sine of 0 is 0. And plus 10. Right, plus 10. And we can solve this for C2. Alright, well this would be what? Positive 2/3 plus 30/3. So that's 32/3. Subtract that. So negative 32/3 equals square root of 47 over 2 times C2. So C2 would be negative 64 over 3 root 47. And that, I don't feel like rationalizing the denominator there. So there you go. All right. And I put this in for C2 and we get our final solution, and I'll just do it here. So now the final solution, all right, the solution of the initial value problem is our equation of motion. X of t equals e to the negative t over 2 times the quantity negative 4/3 cosine of square root of 47 over 2 times t plus negative 64 over 3 times the square root of 47 times the sine of the square root of 47 over 2 times t, and then plus 10/3 times the quantity cosine 3t plus sine 3t. Yikes. All right, but still doable. Right, just like any other non-homogeneous equation. And of course this would be again in feet. All right, and then you could use this to answer any question they wanted about, oh, okay, well, where will the mass be after 1 second or pi seconds or whatever. You're just plugging in different values for t. All right. So again, long one there, and most non-homogeneous equations will take a little time to solve, especially with the initial values to find initial conditions to satisfy. And as I've said in the previous 2 videos on these spring problems, make sure your units are consistent. All right, if the weight of the object is given in pounds, that means your mass is going to be in slug. Then acceleration will be in feet per second squared. Distances will be in feet. Okay, make sure you're using those units. If the weight you're given or force is in newtons, then your mass is going to be in kilograms, and your acceleration will be meters per second squared, and distances will be in meters. All right, so pay attention to all that, because that might trip you up if you forget to translate to the correct units. And hopefully watching me go through this one example here of a driven motion problem, driven motion spring problem. Hopefully watching me do this example will help you when you go over similar problems, similar questions. And thank you very much for watching.